So our next presenter is Hans Strand, Director of Product Management at Net Insight. As Product Manager for Synchronization at Net Insight, Hans has the responsibility for the company's synchronization product portfolio in applications such as 5G in mobile networks and other mission-critical networks. He's a technical expert with more than 25 years in the telco industry and has written several RFCs in switching and routing. So please join me in welcoming Hans to the stage.
Yeah, hello. So I'm Hans Sjöstrand. I work with Net Insight, and I'm going to talk about precise time as a critical national service. It's actually a quite cool story. The story I'm going to tell is Sweden leading the way. And actually, the world is really looking at Sweden, how we did it. Because Sweden developed one of the world's leading time solutions, and then also pointed the way of how to implement it as a national critical service, and make that time service independent of foreign influence, for example, GNSS. We, Net Insight and Netnod, we wrote an article about this, which was published in the 5G magazine. And this is the lead article in 5G magazine. And I've been working with synchronization for almost 20 years. It's very seldom a sync guy ends up on the first page. And there is a QR code there you can scan, you can read it, you can download it later. It was written by Netnod and us together, because the solution is kind of jointly developed. I just came back from Mobile World Congress. Mobile World Congress, it's a crazy place. It's 100,000 people in Barcelona. Essentially, there is only one subway leading to the Mobile World Congress. So it's 100,000 people on the same subway, so it's quite messy. It's 2,700 exhibitors this year, and Net Insight was one. And you have robotic dogs doing backflips out of a skateboard. You have robots giving life advice, like going around with AI and showing things. And you can even take a ride in a car-sized drone with kind of propellers. And we were there, and it's also a place where, I mean, people try to understand the trends in mobile and internet. And a quote from one of the leading analysts was, this is more calm than usual, sober. And then somebody actually said, this is the year of the plumber, because it was a new trend in mobile world. And it was because for all years, it's always been about finding the coolest application, whacking it off, and find another cool application, and try to monetize on that cool application. But this year, people started to understand that I mean, it doesn't matter how cool application you have if you don't have a reliable system that you can trust. And if you don't have the security, you're not able to monetize on all these cool features that radio guys put out. And the main part of this groundwork is actually synchronization. So, I mean, again, I've been maybe almost 10 years in mobile world telling people how important it is with synchronization. And yeah, I have not been terribly successful. But this year was, again, totally different. I think I have 40 customer discussions, and almost none I had to explain why synchronization was important or why you needed to have the synchronization in the network and control your own fate. And also, several countries now are looking of this national time, on how can we provide this time ourselves, and how could we provide this time through the network. Because what has been obvious is that there is an over-reliance on GNSS. GNSS is like everywhere. I mean, you have it in your phone when you're running, you have it in your watches. And it's also the way that mobile networks synchronize themselves. How mobile base stations get their time is very, very often from GNSS. And there was a report from UK recently that they said that if there is a GNSS outage, it will mean £1 billion per day cost to the society. And there was a similar thing written in US a couple of years ago. It was even on 4G time that the cost in US was more than $1 billion per day, whereof half of that was in the telecom sector. And also, I mean, now there is news popping up that, yeah, you see the map here. There was an outage during Christmas. Somebody turned on a GNSS jammer on a boat that was kind of going through the Baltic Sea and whacking out Poland, the Danish island there, Bornholm. We saw it because we have systems there. Netnod noticed the outage, and then it kind of came back again a few days later. So everybody's now are starting to realize that GNSS is extremely vulnerable. And we have one customer which are, I mean, planning to launch their new cool service in stadiums. It's 55,000 people in this stadium. And they have spent quite some time to develop this cool application for the audience. And then you could imagine the kind of engineer going up to his boss to say, I have this plan that I will put a single point of failure in this system. And that single point of failure is a light bulb, 27-watt light bulb, 20,000 kilometers up in the sky. I mean, that didn't fly. So they kind of realized to make this service, it's not about how we install radios in the stadium, it's how do we secure timing to this stadium. And it's an ongoing project because they realize we have to have this, we have to control our own fate, we have to have the timing through the network. Sweden realized this quite some time ago. Sweden's regulator, PTS, kind of mandated our 5G, to get the 5G license in Sweden, you must be or have a system that are independent of GNSS. And then Netnod actually provides this in 6 places. Netnod provides a Swedish national time. And then the 5G mobile operators need to take this GNSS independent time and distribute time in their network. GNSS independence. And this has been called, or started to be called, the Swedish model, because others are looking at us now. We were speaking to a lot of both regulators, governments, and operators in Barcelona about this. And I think Netnod is also having discussions on and giving out advice. I mean, how is this achievable? Because this Netnod part, I mean, you have to create this robust national time. And the first thing, I mean, who will pay for this? Because it's a cost. And part of this cost was decided, it was kind of a joint venture. So part of the cost lies on the Swedish operators, and part of the money comes from the Swedish government. So that is the funding model. And then Netnod took this money and developed this really cool service. And so on 6 places, they are offering what we call ePRTC service. I mean, you don't get to first page to have a cool abbreviation. So ePRTC essentially means that you have 30 nanoseconds accuracy always on these 6 locations. And 30 nanoseconds, that's really, I mean, that's really, really cool. 1 nanosecond is, I usually say, it's a foot. It's the time it takes for light to travel 1 foot. So 30 nanoseconds is the time that it takes for light to travel about 10 meters. And that is the accuracy that Netnod offers in 6 places in Sweden. Not occasionally, all the time. And that requires both skill and equipment. And Netnod have all these because they have built up these skills and this equipment over these years. And now, I mean, it was really, now the rest of the world is kind of looking at us and say, okay, how did you do it? And the Indians has actually succeeded or starting to succeed. The Irish is, well, they are trying. And then there is other countries that are following suit. And then you need to have this national distribution of the time. Because one big problem for a regulator to impose and say, yeah, you have to have this requirement. You have to fulfill this requirement. And then you impose a lot of cost on the operators. And that's not fair. And also the rules must be able to kind of, well, at least fairly be implemented. And this rule, how telecom has decided to implement time is by using PTP and something that called full timing support. It essentially means that every equipment in the network must be timing enabled. So every router, every line card of every router must be able to handle time. And also every line system that supports these routers must be able to support this time. It means a humongous cost to operators. And so regulators are talking with us and saying, okay, I mean, how can is there any way we can solve this without imposing all this cost and trouble? And also, I mean, this is people that control their own fiber. There's a lot of mobile service operators that doesn't have fiber infrastructure, that actually rely on rented capacity, and they don't have routers in the middle. So suddenly PTS imposes a rule that means it's impossible for example, alternate mobile operators to work, and that's not fair. So what is the solution for this? And now enter kind of Net Insight. Because we don't come from the telecom, we come from media and broadcast. And media and broadcast had exactly the same requirement, but a bit earlier, because for some reason, mobile network is not critical national infrastructure. Broadcast network is, or used to be. So in media, we developed a way to transfer time with the media stream. So instead of saying that, yeah, every vendor you have to have timing enabled and full timing support, we kind of developed a way to send the timing. And broadcast has exactly the same requirement, 1 microsecond accuracy in the air interface as mobile has. So we developed a way to send this time with the media stream. So it is as a service. In this way, we cannot separate out the problem to distribute time from the hardware equipment. We call it disaggregate. I mean, it's a cooler word. So we disaggregate timing and this solution. It means that you can upgrade your network and you don't have to put out an RFP filled with 3 pages of timing requirement. You can actually buy the best router or best switch on the market, not the one which have implemented PTP sufficiently. And then also, when you upgraded your network, you don't have to put it in your lab and interrupt test your vendor A or out to vendor B with your timing vendor C, with your optical vendor D, because the timing actually flows through your network as a service. And this solution is a lot more cost effective. It doesn't impose any restrictions on using leased capacity. And this solution has been selected by 2 out of 4 mobile operators in Sweden. And also, ITUT has kind of realized that, yeah, maybe this full-time support wasn't the greatest of ideas. And also noticed that they don't really have a solution. So now ITUT has opened a work item to kind of make this a standard. And we at Net Insight are actively contributing to that work in order to make this a standard, not necessarily our proprietary solution. I'm pretty convinced that Net Insight will be the best implementation of this because we have 20 years of experience of it, but the technology is going to be standardized. So what we call this technology precision TimeNet technology. I will just kind of give a really brief introduction to, and this is not in the article. So the article kind of describes mostly how Sweden did it, more about how Netnod did their part and how we did it, and how regulators are thinking on this issue. So provide precision TimeNet. One customer, they wanted to compare to see, oh, okay, you claim that PTP doesn't do the job. I'll check it out. I will try it. So they took their favorite PTP vendor and run it through the network. And then they tried our network. So in 1 week's time, the PTP guys, it was almost 100 times outside spec. You remember this 1 microsecond requirement. They were almost at 100 microseconds time error. While in a week's time, the precision TimeNet technology over the same network never exceeded 500 nanoseconds of time error. So that was a real proof to them. And again, this takes both skill and technology. Because, I mean, you have to handle a lot of noise in the network. We have adjustable rates, so we can send with PTP, you're kind of confined. You're supposed to send like maximum, I think 64 is the packets per second is the maximum that is usually used in PTP. We send 8,000 timestamps per second, and we can adjust that. I mean, for example, if you don't have the bandwidth, we can decrease it if the link is not that noisy, if there's no need. And we can also adjust packet sizes to not end up in buffer-related issues and things like that. And we also have very intelligent filter algorithms that work on network level. And then also we don't have any what the PTP guys call best master clock algorithm, which is a really bad idea, to find the best way through the network. I mean, because what you want to have, you want to have to synthesize the clocks. You want to have several paths and use active protection and then collaboratively synthesize these clocks together. So in that way, we are able to do a lot better synchronization over a troublesome network than any of these best master clock guys. And also, the greatest evil to synchronization on a network is what I call asymmetry. It is, if you have a change in the underlying network, let's say you have an optical network and suddenly the DWDM decides to kind of reshuffle things, then you get a change in latency, and I mean, these are completely independent. What the transponder in Kalmar thinks about life and the transponder in Stockholm, that they are completely independent of each other. So if there is an event, outage or a reboot or software upgrade, it will start off and with a totally new delay profile in both directions. So it will create a new asymmetry and a new timing. So in this example here, there was a network event, and the round trip time suddenly just changed 15 microseconds. So again, the PTP guys, they would have followed that change and probably been about 7 microseconds off suddenly, without anyone really realizing what happened. But we have algorithms that detect change. So instead of kind of welding in things in every machine to avoid change, we actually embrace change. We detect change using software. And software is possible to virtualize. Mobile guys like that. I mean, they like the virtual DUs and software. And it's possible to also implement on a network scale. So we can detect, and when we detect an asymmetry change, we don't follow it. We kind of just relax a little while, let it settle, and then we kind of measure up the new asymmetry, and then we lock again and start working. So absolutely nothing happened with the time signal, despite that there was a quite significant network change. And so in a wide area network, there is asymmetries, there is traffic variations, and traffic variations is also evil because they are very often, especially in mobile networks, they are extremely asymmetric. I mean, everything is almost downlink. So you get this effect. I mean, and what you see here is the day variation. But if somebody's, I mean, in Värmland starts a hockey game, I will guarantee you that you will see a totally different kind of latency profile on the network than you did before the game started. So it's essential. And normal traffic doesn't notice this, but this is extremely, you remember the nanosecond. This is extremely important for timing. So we are the kind of odd birds on the network. So, and also packet delay variation. It constantly happens. You TCP guys, you don't care really, because you just take it in a buffer or handle it. But we sync guys, we really suffer from this. So in this way, to handle this on a network scale, and again, I mean, it's not about making 80% of the mobile base station work. It actually has to be all the mobile base stations all the time. Then you have to have quite powerful real-time control systems on a network scale. And again, these are possible to virtualize because it's just software. So you have to handle packet delay variation, you have to handle traffic variation, and you have to handle the asymmetries in real time. And then sometimes you make a mistake. Sometimes you're super cool. Maybe this hockey game was buried in a lot of other software traffic, so there was a lot of noise, and we missed that kind of asymmetry change. Then you have to have kind of an orchestration system to kind of monitor this. So our system, we learned this over the years, kind of provides 100 metrics per second, creating a data lake of information about nanosecond resolution of the time, unidirectional time in both directions, the variance of that time, the delay percentiles of that time in order to analyze it, and then on an orchestration level, kind of realize, oh, there was an event, I missed that, that doesn't look good, and then fix that. So we have been running a pretty large network in Turkey over a year. We have Fredrik, the hero here in the audience. He's been analyzing that network for a year, and I guarantee you there is things going on in a Turkish network. So you have to kind of constantly be able to monitor. And we've been able to provide a pretty stable sync in almost entire Turkey with almost zero GNSS coverage, because Turkey is like between Russia and Syria, which is not a good spot to be if you intend to rely on GNSS for timing. And so I really, really recommend to read about this Swedish model. I mean, to be a little proud being a Swede, it's about precise time, and you have the QR code there. It's the 5G magazine from TechNexus, and it's jointly written by Netnod and NetInsight. Yeah, that was, thanks.
So we have a few minutes for any questions. Are there any questions in the audience for Hans on this? Everyone's scanning the QR code frantically.
Yeah.
Scan away. Any questions?
It's not that often you read cool things about synchronization, so I really recommend it. You can be the next cool guy on the next event.
Okay, we just give you a minute to scan it. Okay, then if there are no questions on Menti or in the room, let's please join me in thanking Hans for an excellent presentation.
Thanks.
Thank you so much.
Thanks.